We like Numpy because it combines the accessibility of a mathematical syntax with the efficiency of low-level code. So here I've created an array of 1,000 by 1,000 numbers, and I can do simple operations like grab the first few elements, or compute the sum, or do something more complex like add x to its transpose and subtract off the mean in some direction, in some axis. And these operations follow a standard mathematical syntax, which is accessible to a broad set of scientific users, and they're also decently fast. They're written in low-level C. Unfortunately, just as these virtues gave rise to the scientific Python ecosystem, Numpy has a limitation, which is that it doesn't scale very well to data sets that don't fit in main memory. So here I'm trying to allocate a 100,000 by 100,000 array, and Numpy gives us a memory error. It says, no, sorry, I can't operate sensibly in this regime. Fortunately, we do have distributed clusters that do have enough memory. We need to find some way to implement the same Numpy API across those clusters. So I'm connected here to a cluster on the Cheyenne supercomputer. It's just a small part of it, got about 1/3 of a terabyte of RAM. And I'm using a project called Dask Array. So Dask parallelizes a variety of projects. One of its subprojects is Dask Array. And Dask Array implements a broad subset of the Numpy API. So this code would not have worked previously, but instead of using Numpy, I'm going to use Dask Array. So one Dask array is composed of many different NumPy APIs, many different NumPy arrays spread around a cluster. So here I'm telling Dask array, please construct for me one logical array, that's 100,000 by 100,000, that's composed of many, many small NumPy arrays, each of which is of size 2,000 by 2,000. I'm going to ask it to persist that on my cluster. On the left here, we're going to see all of the workers of our cluster create all of those small NumPy arrays. So each little bar here, each line corresponds to the activity of one core in our cluster, of which there are 300 cores. And this is what they're doing over time. So for these 58 milliseconds, this particular core, this row, was running a function to create one random array. And so we have this large array throughout our cluster, and we can easily do operations the same as we did before. We can get a few rows. We can compute the sum. So the API is the same, but now they're being implemented very, very differently. So here, we spent most of our time doing coordination and communication. Red is communication between different workers. Most of the cost of this operation is communicating small intermediate sums between each other. And we can also do more complex operations like add x to its transpose and subtract off the mean across some axis. In this case, we don't want to compute the result. We can't actually store that locally, but we can also ask Dask to persist that in memory as well. And so this is a very communication-heavy computation. So on the left here, we're going to see that there can be lots of red, a lot of communication-heavy tasks. So there we go. So Dask Array gives you the same NumPy API using NumPy under the hood, but now it's on across a distributed cluster, allowing access to much, much larger data sets.